Thank you, Luca. Good afternoon, and thanks everybody for having me today. So I'll be reporting on some of the things we've been doing on AMR as part of the Mood project. But before anything else, I'd like to thank very much the former members of my team who contributed to this work, in particular Katie, Rania, and Alex, who were supported by Mood directly. So what do we do? Mostly, like everybody else here, we do maps of disease, but we try to do that on a global scale or at least a regional scale, like the scale of a continent for the most part. So perhaps a small word of context. I'll present our general approach of what we were doing before Mood, and then I'll focus a bit more on Europe specifically, and I'll finish by some aspect of disease dynamics applied to AMR in Europe. And maybe a point of context here, we actually started working on low and middle income countries. And we were approached by the Mood partners to tell us, do you want to join us to do something similar with your fine scale mapping in Europe? And the connection wasn't obvious at first because Europe has quite good systematic surveillance system for AMR, so it wasn't entirely clear what we could add to that. And I'll try to show you that we can perhaps add something. So in Europe, we have these amazing systematic surveillance systems for almost 40 years in some Scandinavian countries. Across most low and middle income countries, that does not exist. There's one LMIC, to my knowledge, which has a systematic surveillance system that reports AMR data publicly, and that is Colombia, talking as of 2017 when we started this work. So we had to rely on sort of alternative source information. And that's mostly point prevalence surveys, so small surveys that are done usually in the vicinity of a veterinary institute by taking samples from a farm or more frequently from a market like here in China. And microbiologists often do that to find out about resistance level in the area, but mostly to find out about new resistant genes, because that's the cool thing for them to find. But in so doing, they do estimate prevalence of resistance for different drug-bug combination in different parts of the world. So we took advantage of those surveys. We looked for 4 indicator bacteria. That's E. coli, that's fine. E. coli, Campylobacter, Staph aureus, and Salmonella. We looked for it in chicken, cattle, and pig, which together represent about 95% of the terrestrial livestock biomass. So if you know what's going on in those animals, you mostly know what's going on around the world. And then we looked for drug-bug combination, recommended for susceptibility testing by the AGISAR consortium of the World Health Organization. And when we started this, we did the first version with 900 surveys that we read and from which we extracted data. As of today, we are around 2,000 surveys in our database, which I'll show in a moment. So once we've extracted that information from all these surveys that we read by hand, we can put everything on the map. And now a little word about what metric we're concretely looking at. In each of those surveys, you're going to have a panel of antibiotics that are tested for resistance. And a certain number of samples is going to be resistant to that. What we do is counting the number of drugs for which we reach more than 50% prevalence of resistance. So it's a proportion of drugs that are failing in each survey. And that's what the red dot on the map represents. Altogether, that's around 12,000 resistance prevalence estimate and around 300,000 biological samples. Now, for the next step, we want to move from point level information to continuous coverage of prevalence of resistance. To put it in words, we just say that resistance in one point, in one place between the points is going to depend on resistance nearby, depending on some spatial weights that we're going to try to estimate, as well as the effects of additional risk factors that can locally modulate the intensity of resistance, like antibiotic use, the stocking densities of your animal, temperature, travel times, and things like that. Now, in practice, we do that using ensemble modeling. So we're going to use a lot of the covariates, some of which were assembled by Willy, to try to make a first prediction of this value of P50 in every location. And typically, we're going to use boosted regression trees, GAMs, lasso regression, and now we use neural networks as well. And in the second step, we're going to use universal kriging as a mean to ensemble those predictions. The main trick here is to try to capture the residual spatial correlation that we may that we may have in the data. And then we make an ensemble prediction of with all of these models together, and this is how our results look like. So, oops, sorry, how do you go back? Yeah, so of course you can zoom in to see in which part of the world the situation is the least ideal. And in South America, we had the biggest hotspots of resistance in animals in Uruguay and in the south of Brazil. In Africa, it was mostly in the suburbs of Johannesburg and in Ethiopia. And in Asia, generally speaking, the levels were much higher than everywhere else, but in particular in South India, South China, and Northeast India. And in the same spirit as what Guy just presented, we make all of what we use available. By all of what we use, I mean both the input data, so all the data that we extract from the point prevalence surveys. You can go there, click on the map, you have all the info about the resistance to every drug in every location. There's a link to the original survey. And you can also download our output, so the underlying prediction map. The red map, we have this for terrestrial animal and also for freshwater aquaculture. And this was the work of Nico Priscolo in my group. So that was our starting point, sort of joining the Mood project. And so what did we try to do after is apply the same sort of reasoning in Europe. And yeah, the reason why we didn't start in Europe was because EFSA exists. And so EFSA, for a certain number of years now, has been compiling data on resistance in animal and food products as well, I believe. And we thought, okay, how can we try to leverage the granularity of point prevalence surveys and try to combine that with EFSA data? So concretely here, we looked for all the point prevalence surveys published in Europe between 2000 and 2021. And we're quite surprised to only find sort of 200 surveys that match the same inclusion criteria that we had for low and middle income country. And perhaps this low number of point prevalence surveys is attributable to the fact that, you know, since we have surveillance, scientists go less out of their way to find out what's going on in terms of resistance in their areas. And then, yeah, we combine that with reports from EFSA, sorry. Yeah, there we use information between 2010 and 2022, extracted a lot of information from those PDF reports. Now the trick for the slight adaptation to the methodology here again, we train some geospatial model, BRTs, LASSO GLM and LASSO CAM. We assembled them this time using AUCs as ponderation because we did not find much of a spatial signature, so not much spatial correlation in the data. But the crucial step is that we try to make those maps that we have here at the second step, we make them EFSA compatible in the sense that if you sum the value of all of the pixels over the map, you should rebuild the mean that's reported by EFSA for a given country. So effectively what we're doing is just a disaggregation exercise. And so this is how our result look like for different pathogen. So the highest resistance values were in Campylobacter, followed by E. coli and Salmonella. In terms of hotspot for this P50 index, so we use the same index to map. We here put an artificial threshold at the 95th percentile of all the values that we mapped, and that enabled us to say a few things about where we find the so-defined hotspots of resistance across different countries. So for E. coli, we had high levels of resistance, mostly in southern Romania and the southeast of Italy and the Po Valley. For Salmonella, mostly southern Hungary and northern Italy and central Poland. And for Campylobacter, there's really one epicenter of resistance for Campylobacter in Europe, and that is Spain. So the vast majority of the pixel categorized as hotspots of resistance in Europe for Campylobacter were in Spain. Now, if we compare data sources a little bit more closely, and this is only over the last 3 years of data, for E. coli and Campylobacter, we generally had higher level of resistance associated with those point prevalence surveys compared to the EFSA data. Whereas for Salmonella, things were a bit less clear. There were discrepancies. but it could go both ways, one being higher or lower than the other. And we hypothesized that the high resistance associated with PPS could be the result of sampling towards estimating resistance in sort of higher end drugs, especially in the later years. Has been really a focus for sampling for colistin resistance in particular. And now, in terms of the discrepancies between EFSA and PPS, there's also sort of systematic difference per country. The same bias, of course, could apply that there's more targeted sampling towards high-end drug in certain country, but we found it somewhat interesting that in Portugal and Switzerland, the PPS tend to underestimate resistance compared to what is reported to EFSA, whereas in Poland, Germany, and Spain, there tend to be an overestimation of the resistance level in EFSA versus PPS. And so a few take-home message about the state of resistance at subnational level in Europe. I think the first thing we have to tell ourselves, and it's not to pat ourselves in the back, is that if we compare to efforts to try to document resistance in other parts of the world, we do a relatively good job in Europe. I think it's good, and we should be happy about that. There is quite a bit of data, and it is quite a bit available, I would say. The formatting of the data at EFSA is certainly not perfect. We wish there were more frequent sampling. Not every species is sampled every year by EFSA, for instance. Nevertheless, it's there. And I think if improvements have to be made in Europe, it would be about making all of that data more machine readable. At the moment, it's a lot of time spent on PDF, and I think it's annoying for everybody to produce those PDF and then to read them. And to make it a bit more granular. I know some countries have released national level reports at national data at subnational level, but it could be great if this could be integrated on a European level, I think. I think PPS can supplement EFSA to map data within countries while preserving national AMR levels reported, so it's not a competition because we are EFSA compatible. But I wonder, if while also preserving farmers' privacy and respecting those constraints, we could at least try to report EFSA data at NUTS 1 level, for instance. And then, there's discrepancies in AMR prevalence between PPS and EFSA. I think this really warrants further investigation into understanding a bit better the process of how and which sample is chosen to be part of the EFSA report in each country. And in particular, Campylobacter and PPS seem to be systematically higher than what is reported to EFSA. And now to finish, I'll talk a little bit about the work we did on dynamic modeling of AMR and the intervention in Europe. So we tried to look at two different things here. Restrictions of movements of animal and products, so that's essentially restrictions on trade, and restriction on the prices of antibiotics. So the former is still ongoing, but our preliminary results are a bit boring in the sense that from what we've explored so far, trade alteration does not seem to have much of an impact on AMR levels in Europe when you compare it to strong domestic intervention on antibiotic use or on the transmission rate. So we to have intervention on levels of biosafety, for instance. And this has trade really has a truly negligible effect compared to what we've seen in terms of domestic intervention. So I'll be talking about something else that we did as part of the project, which is intervention on the price of antibiotic. And that's a polite word to say applying taxes. And here the story is a bit more nuanced and interesting. So where does the idea of taxing antibiotic comes from? It's simply an application of the polluter pays principle. You create an externality by using an antibiotic, and in this case, there's a loss of antibiotic effectiveness for the general population by overusing the antibiotic, and one should pay for that, or at least that's the idea. The idea doesn't come out of nowhere. It's been used, for instance, in Denmark. The more toxic a pesticide is, the more you're going to pay to use that pesticide, and the hope, of course, is to orient the use towards other pesticides that are as little toxic as possible. So we wanted to apply the same principle to antibiotic use in animals to reduce resistance. What's not entirely clear is if, like with pesticides, should we tax more the antibiotics with high resistance in order to limit the use now, or should we tax more the antibiotics with low resistance level in order to keep them available for as long as possible? And the answer to that question is not straightforward because you have some epidemic kickback, and it's a highly nonlinear dynamic that you have once you start varying the intensity of antibiotic use. And that's why you need to combine economic consideration with disease dynamic models. So for today's argument, I'll use a simplified version of this model that was developed by Alex Morgan, who was in my team. So each box represents a fraction of the population, and you can move from a susceptible state to an infected state with a wild-type infection. And if treatment fails, you'll move to the fraction of the population that's resistant to either 1, 2, or 3 drugs. And for simplicity, I did not represent the fact that, of course, you can, that you can, that would be easier like that, that you can recover from each of those classes. Thanks for the eyes, Luca. I hope it makes sense now. Okay, well, okay. Now let's combine this with a bit of basics economics. So how is the quantity of antibiotic use be influenced by the tax, and how is that going to affect the amount of antibiotic use? So let's introduce the notions of price elasticity and cross elasticity for those of you not familiar with that. So an elastic good is a good like coffee. Basically, if the price changes, the quantity demanded is going to change quite as rapidly because you don't really need it. I do realize that using Starbucks coffee as an example of an elastic good in Italy may not be a good example because you as civilized people, you would not buy this anyways. In any case, an inelastic good is something for which if the price changes a lot, the quantity is not going to change. If, like me, you have a 1.5-year-old baby and need to buy nappies, no matter what the price of the nappies, you will buy the nappies. And now there's also the fact that the quantity demanded may change based on another good. So typically, an inelastic cross elasticity would be the baby cream with the Pampers, and an elastic cross elasticity would be the example of 2 drugs that can be substituted for each other. If one of the 2 is cheaper, you'll go for the cheaper one that has exactly the same effect. Now, the way we try to express this is with these sort of matrices of elasticity and cross elasticity. And we place ourselves in a situation where we have 3 antibiotics, and we imagine that the antibiotics have an increasing degree of importance. So left one, you'd have first-line treatment like a penicillin, and on the far right, you'll have something much more high-end like a carbapenem. And basically, what we say is, to make a long story short, we say that basically, if I tax one antibiotic, this will drive down the usage of the given class and drive up the usage of the non-taxed classes. Now, there's several ways you could decide to tax the antibiotic, and that's really the core of the experiment here. We can combine our elasticity assumption with this dynamical system that is the disease dynamic model, and we're going to try to do 4 different things. Option 1 is you put a flat tax at 50% of the value on all the antibiotics. Same tax for everybody. Option 2 is a single tax on a single antibiotic with either the highest or the lowest resistance level. Option 3 is what is called a differential taxation, where you would scale the taxation proportionally to the resistance level of each of the drugs. So your middle class is not taxed more or less than 50%, but the more resistant one is then taxed more, and the lower resistance one is taxed less. And then finally, we can compare everything with an outright ban on a certain substance, so you're not going to use any of the substance. That's actually what's happening now in the EU, for instance. We have certain category of drugs that are completely banned for usage in animals. Now, the way we compare these policies is by measuring the decrease in the average resistance as a percentage of reduction of antibiotic use resulting from each of the taxation scheme. And long story short, we measure the impact for each taxation scheme for 50% value tax for a range of epidemic parameter. And rather disappointingly, all taxation schemes are roughly equivalent to reduce resistance as long as you target the high resistance antibiotics. So answer to the question I first brought, you should tax the high resistance one. If you're going to tax by a certain amount, you get better result by taxing the high resistance one. But the more important message here is that taxation would have similar effect size, if you look on the far right here, to the bans that are currently implemented for certain substances in the US or in the EU. So basically, you don't do much better than having the current bans that we have. So the question is, well, why would we bother with introducing a tax if our regulations are doing the job to keep resistance down, right? Well, because taxes generate money, and that can interest someone potentially. Now, to estimate the revenue that comes with that, we have to make very crude assumptions. First, because animal health companies, they will never, ever tell you how much they sell their antibiotics, basically. And so we had to go to the shop ourselves, so to speak. So we split the world between high and low and middle income country. As a proxy for high income country, we took the market prices on online pharmacies in the US. And as a proxy for LMICs, we take the market prices in China. And this was work done largely by Cheng Zhao, who's really spent hours and hours and hours basically going on Alibaba and on pharmacy website in the US to try to get prices for different categories of drugs that are frequently used in animals. And then we combine that with information on the total amount of antibiotic used for different classes across different countries, which is something we've been working for a while for in my team. And we make that compatible with the total of antibiotic use reported by continent by OA, who does these reports annually as well. And so if we were to apply a global 50% value tax in a differential taxation scheme, this is how the revenue would look like. So we could expect something around $1.1 billion each year. And there you have to take a moment to pause and compare that to the price of drug development. So bringing a new antibiotic to market is estimated to cost between 1 and 2 billion a year. So we could generate money that's sort of on the same order of magnitude as the cost of developing a new drug each year by taxing antibiotic, and put that in perspective with the fact that there have been no new classes of antibiotic discovered for the last 30 years also. But the interesting part here is in terms of where does the money from the tax would primarily come from? Mostly from high-income country, because the price of antibiotic across LMICs based on China as a proxy are extremely low. So basically, although they use 80% of the antibiotics in the world, LMICs would only contribute some 20%, a few percent, so the 50 million every year to that global pot of money created by having a tax on veterinary drugs. And so this leaves us to conclude with a few sort of outstanding questions. Would it be fair that high-income countries contribute more to a global fund despite using less antibiotic? Is it fair that high-income countries contribute more because they historically benefited from using antibiotic for 60 or so years uninterrupted, which has enabled developing industrial agriculture as we have it in our countries? Should farmers support the cost of developing new drugs? I think no. I think they can chip in, but I think they should not be the scapegoat of overusing drugs in general. And what about permit trading? One of our co-authors on the paper really insisted in exploring that route too. Permit trading essentially, you set the amount by which you want to reduce the size of the antibiotic consumption, and then farmers get a permit to use a certain amount. And if they don't use it, they can sell it to somebody else. So it's like the Kyoto Protocol. It hasn't worked so well for climate change, I think. But in theory, that's also a system that could work. So lots of outstanding scientific and ethical questions left, and thank you.